My name is Molly Francis, and my topic is the evolution of MRSA. MRSA, MRSA, is an abbreviation for methicillin-resistant Staphylococcus aureus. MRSA is resistant to methicillin and other beta-lactam antibiotics. Beta-lactam antibiotics are those that have a beta-lactam ring in their structure. Beta-lactam drugs are among the most commonly prescribed. Within this drug class is also penicillin. MRSA has been called the leading cause of death from a single infectious agent in the United States. It is often contracted in healthcare facilities like hospitals and nursing homes. However, it can also be community acquired. Common modes of transmission are skin-to-skin contact and sharing of equipment and tools. It can be highly virulent depending on the strain and has a wide variety of symptoms. This wide variety of symptoms comes from the fact that MRSA can affect so many different parts of the body. Staphylococcus aureus can obtain resistance through a variety of mechanisms. Bacteria who produce penicillinase, which is an enzyme that cleaves beta-lactams, can resist methicillin by partially hydrolyzing it. It can also alter penicillin binding proteins, which are the target sites of beta-lactams, by decreasing their binding affinity. So they have a low affinity, they don't want to bind. The most prevalent mechanism, however, is the acquisition of an extra PBP known as PBP2'. MEC-A is the gene that codes for PBP. It is only present in MRSA. The PBP is only present in MRSA. Therefore, it is used for identification of MRSA in the lab. And here is a picture I found, which I think is quite funny. It's the little MRSA with his two little MRSA parents, Mr. and Mrs. MRSA. They're telling him, remember, Junior, say no to drugs, obviously like methicillin. So where did MRSA come from? Before MRSA, there was penicillin-resistant Staphylococcus aureus. This first popped up in 1942, and it obtained resistance through the production of penicillinase. By the 1950s, it became pandemic, so methicillin was produced in response. In 1961, however, the United Kingdom reported a case of methicillin-resistant Staphylococcus aureus, and many other countries began reporting the same. The evolution of MRSA. So the MEC-A gene plays the biggest role in resistance. Nucleotide sequencing has shown the gene to have homology to two distinct genes, the penicillinase BLAZ gene and the E. coli PBPS2 and 3 genes. It has been proposed to have emerged by a homologous recombination event of PBP and beta-lactamase. This recombination event would have been the transfer of the MEC region between lineages. Transfer being the movement of genetic info among bacteria, which includes resistance genes. And MRSA in the context of natural selection makes sense. When these drugs started to be widely used, strains that could code for the PBP2', who had a MEC region, survived, and therefore bacteria with the PBP2 became more prevalent. So there's much danger in the overuse of antibiotics. Antibiotic use in human medicine and agriculture continually selects for resistant bacteria. The success of the pharmaceutical industry and the ease of access to antibiotics has made us kind of become complacent and forget about the dangers of antibiotic resistance. Antibiotics will no doubt become more numerous and more will be needed as bacteria continuously have an uncanny ability of being able to overcome the drugs that we put out. Resistance has already been shown in some cases to vancomycin and daptomycin, which are the only two drugs that can be used to treat MRSA. So it really lies in the hands of physicians to not overprescribe antibiotics, to not give antibiotics to patients who have viral illnesses because they have no effect. Patients often demand these, but again, the physician can really play a big role in lessening antibiotic resistance across the board. So it's important that we continue monitoring resistance. We can definitely get into a very, very tricky place if this continues to go on. I hope you enjoyed my presentation. My topic again was the evolution of MRSA. Thank you.